Okay, so this is lecture 22. As I told you just before, we will continue our lecture up to lecture 28. So that will be the last lecture in this semester. So we have 6 more or 7 more lectures, including today's lecture. So after finishing the drift diffusion scheme, so successfully discussed all about that, then now we are now discussing more implementation related topics. So previously in the previous lecture, lecture 21, we have introduced the concept of discretization of our structure. So we introduced some mesh related topic, and typically, mesh-related topic is regarded as something which is inevitable to perform a numerical simulation, but which one is not at the center of that problem. So, if you have good mesh, you like it and you can just use it. But generating a quality mesh is particularly very difficult for three-dimensional structure, so that we need certain expert to be devoted to that topic. Fortunately, in nowadays we have well developed mesh generators, so that's the reason why as a student in this field we can just rely on already made mesh generators. So I will not talk about how can we generate the mesh. So we will think that anyhow the mesh is given, then how can we import it and how can we calculate the required coefficient for our mesh. All of these slides is just taken from the previous one. So however, let me just really quickly review it. So our equations are given in this generic form. So divergence of a certain vector field is given by a scalar source term. So when we integrate it over certain volume, frequently called as a box or finite volume, then we will have the integrated form. Actually, the selection of this omega, so small box or small volume, is really arbitrary. However, since we have so many points inside our system, our domain, so anyhow we need a well developed way to divide our system into small volumes. So we can have many different points, and ask me that question: how can we divide? Let's say that this is the domain we will use for our simulation. Then how can we divide, or how can we introduce our omegas for each node? So this one, for this one, this one, this one, this one. What will be the reasonable choice for selecting omega for each node? That is our concern. So in this case, the natural way is assign the Boronoid cell as our volume or box omega. So for each node, just to assign its Boronoid volume, then everything becomes quite clear. So Boronoid cell, once the nodes are given, so if we have a list of points, point 1, point 2, point 3, point 4, and the last point, if we have a list of points, then we can easily calculate, not easily, but anyway, we can calculate the Boronoid cell for each node. It is guaranteed. But here we have another condition, is that when we just assign Boronoid cell to each node, in order to this Boronoid cell gives us a physical meaning, then we need a condition of Delaunay mesh. So I just showed in the previous lecture. I just show you what does it mean. Here we have Delaunay mesh in the left and non-Delaunay mesh and right. And here you can see that anyway, if we have 6 points inside our system, let's say we have 6 points inside our system, then we can always assign each Boronoid cell to each node. For example, for this center node here, this large dot, we can find the Boronoid volume like this. This is the correct Boronoid volume for this center node. And in this case, in the case of Delaunay mesh case, when we build the Boronoid volume, then for this Boronoid volume, we can always find that this surface of this Boronoid volume is related to always a certain h. Okay, so if we have a certain h and surface of our Boronoid cell, they are correspondent to each other. So if we have a certain side or surface of a Boronoid cell, then we can find a one-to-one relationship between H connecting the center node and surrounding node. Good. But in the case of a non-Delaunay mesh, even in this case, we have 6 points here. 1, 2, 3, 4, 5, 6 points here. Then even in this case, we can find out the Boronoid volume. It is always found. So this is a correct one. There is no mistakes. So this red box is Boronoid cell for this center node. Correctly calculated Boronoid cell. So assigning the Boronoid cell to each node, that doesn't make any problem. But point is, if we have non-Delaunay mesh, then the one-to-one correspondence between surface of Delaunay mesh and H is now broken. For example, here we have H, and here we have surface. It's good. Still, we have one-to-one correspondence. And how about this? Here and there, we can find it. Also, here and there, we can find. But point is, if we have this non-Delaunay mesh, then for this H, we cannot find any surface of Boronoid cell corresponding to this H. So let me just come back. When we assign the Boronoid cell as a box or control volume for certain node, then this procedure itself is always guaranteed. You can always find the Boronoid cell, then you can assign it to each node. It's good. It is guaranteed. But whether it really represents physical meaning or physically sound description or not, that is determined by whether your mesh satisfies the Delaunay mesh condition or not. So that's the reason why people, when they are talking about mesh, always ask whether this mesh has Delaunay condition or not. Okay, but fortunately, I think that when you are working with your system, your structure, Delaunay condition is satisfied not by yourself, but your mesh generator will give you the Delaunay mesh, so you are a little bit free from this important problem. Okay. Now we are going to the Poisson equation, the specific example. And here we have a Poisson equation, and if we have to discretize the Poisson equation, first we calculate the surface integrated form. So here we have the flux, so in this case displacement and infinitesimal area component, then we make it the area or surface integral. Then the Boronoid cell. This is Boronoid cell omega for center node not here 0, and this is round omega corresponding to the surface of our Boronoid cell. So surface integral now just decomposed into 5 pieces, because this Boronoid cell have 5 surfaces. So we can find 1, 2, 3, 4, 5. So this surface integral now becomes just a summation over all surfaces and the flux normal to that surface and the area of that surface. The product of these two terms just yields here the integrand. And here we have f function, and this is a flux from 0 to I. So 0 to I means that if we have my eraser is not working properly. Okay, here the direction is starting from here to there, here to there, from 0 to 3rd, 4th and 5th. So in this case we have to calculate phi I minus phi naught, and here we have a minus sign. Okay, so now we have Poisson equation, and then I just show you the recipe to calculate for example A0I component. Of course this is not a standard notation. There is no standard notation for this quantity, so there are many different ways to denote it. The point is, so how can we find the area of a surface in a Boronoid cell? That's the main question. Of course we have to also know the distance or length of an edge connecting node I, node 0 and node I. So this length is also important. However, calculating the length of an edge is quite easy. You can just use coordinate of this point and that point, and you can easily find the Euclidean distance. So that it's not a problem. That is really easy. Point is, only a difficulty comes from the calculation of this surface area. How can you calculate this surface area? That is our concern. That is not a straightforward way. So then this is the recipe for our 2D problem. For a 2D structure, it's not very difficult. So think about this one. We have a certain triangle, and it has three sides, and their lengths are A, and let's say B and C. And if we have A and B and C, then we can easily calculate the radius of circumcenter. So here and here, yes, this is the circumcenter. This point is the circumcenter, and this is corresponding to circumradius and circumradius, and this is a circumradius r. So by using this expression, we can easily find the r, the circumradius r. The area of a triangle can be easily calculated from its coordinates. It has 3 points, and we know from the beginning we know the coordinates. So calculation of the area is really easy, and from beginning we know A, B, C. Yes, we know it. So we know them. So from this formula, we can calculate R equal to ABC divided by 4 times area. That is readily available. What we have to calculate is the length corresponding to this one, this blue one, and also this blue one. We need to calculate these quantities. So how can you calculate it? If we just magnify the view for our triangle, for example, in this part, then now why don't you just go to our sketchbook. Then now we have this one. Here we have a certain point, and this is length A, and this is the midpoint, and we have a normal line. So, and if we just keep this normal line, anyhow we will meet the circumcenter. Distance between our corner point and circumcenter, that is by definition the circumradius r. Circumradius r. So this distance is a, and obviously this radius is just a half a. Then what will be the length of this normal line? You can really trivially understand by applying Pythagorean theorem. So r square equal to square of halfway plus square of this green line. And this green colored line is really corresponding to our A quantity, the surface area of, although this is just two-dimensional, so just a line. However, anyway, this is corresponding to the boundary of our Boronoid cell. So from this relation, we can easily calculate this quantity, and this quantity is used to evaluate a sub-0I quantity. So this is one thing we can easily find out. Of course, we are now talking about a certain triangle, and for two-dimensional structures, usually a certain edge, if we have a certain edge, then usually it has two triangles. It is quite certain that it has two triangles at most and in general. If we have just a boundary node, then of course we will have just one triangle attached to our edge. However, in many cases for internal edges, then always we have two triangles. So whenever we calculate the internal quantities like a sub 0 I, then we have to consider this one triangle and another triangle, so and then merge them into one quantity. Or if we are careful about material difference, then we can just keep two different quantities, the A quantity for this triangle and A quantity for another triangle. It is also okay. Okay, so that is quite simple in principle, so you can calculate it. Then I have prepared a toy example. Consider a triangle, and let's say that it has an angle here. Its angle's magnitude is theta. And it has two sides and whose lengths are 1 and L. Of course, L can be larger than 1 or smaller than 1. It is just a positive real number. We can have arbitrary a triangle. For example, if we have an acute theta and very small L, then what will happen? Then we will have such a triangle. If we have still acute theta, so acute means that smaller than 90 degree, and L is larger than number 1, then what will happen? In this case, we will have a long line like this. Then we will have such a triangle. And if we have right angle, then we will have also another triangle like this. That will be another triangle. And another possibility is having an obtuse angle, obtuse theta. Then theta here, obtuse means that larger than 90 degree. Then we will have such a one for small L value, or if L is large, then we will have this triangle. Sorry about my ugly drawing, but I see that you can imagine this situation quite easily. So then what will happen to our circumcenter? So in the previous one, we didn't calculate the circumcenter, but in this toy example, in order to make educational purpose, I just try to calculate the coordinate of its circumcenter. So you know that in previous recipe, we don't have to actually calculate the coordinate because we were able to avoid to calculate circumcenter. But for this simple toy example, let's just do it together with me. So then how can you calculate it? My suggestion is just to assign 0,0 without any loss of generality. And here let's say that this is corresponding to 1,0. And this is theta and the length is L. So the coordinate for this point is simply given by L times cosine theta and L times sine theta. Yeah. Then how can you calculate the circumcenter? Circumcenter is given by intersection of three normal lines. So actually we are allowed to just calculate intersection of two lines. So fortunately, by assigning the origin and 1,0 to for our 2 points, then we can find a very good expression. One normal line should be given by x equal to half. That's it. That is one thing. So the remaining thing is just to calculate a certain normal line or a certain normal line and just to calculate whose x coordinate is given by 0.5 or a half, then we will get the solution. So you know that you can easily understand that will be more easier than this one. So I will work with this one. Then the midpoint here will be just half L cosine theta and half L sine theta. Yes. So we wanted to build a line which cross this midpoint, and its slope is given by tangent theta minus 90 degree, because this is just this is just theta, and the line which is perpendicular to this line should have a slope like theta minus 90 degree. So the angle should be theta minus 90 degree, and the slope should be tangent over that angle. So now just write down the expression for this normal line. It should have tangent theta minus 90 degree multiplied by x minus even so half L cosine theta plus half L sine theta. So this is the expression for this normal line. And in order to calculate the coordinate of our circumcenter, we have to insert a half to, here we have to insert just a half, because this is corresponding to another normal line generated from this edge connecting origin and 1,0. So now we can say the coordinate of our circumcenter is given by half, tangent theta minus 90 degree times half minus something plus half L sine theta. That will be the expression for coordinate of circumcenter in triangle. So since this is the coordinate for our circumcenter C, so now we can say that for this edge, the A parameter will be given by just this one, and for all other quantities, so for all other edges, also using the coordinate of our circumcenter C, we can easily calculate all of them. So this is more explicit, and usually that is not used explicitly. So more frequently we just try to avoid the explicit calculation of circumcenter because that costs more. However, you can do it. So let me just go to a simple demonstration. So I have prepared this simple code. Can you see it clearly? So I have intentionally magnified the font size, increased the font size. So I'm still afraid that is too small to read it. So can you clearly see the letters in the screen? Okay. Yeah. Then here I have prepared one simple, really simple, really simple thing. So here, now say that let's go to our number 6, line 6, and here L is determined as just 1. You can change it, and theta is given by 45 degrees. This is just converted into radian unit in this line 7, and we have 3 points, and these 3 points are just written here, 0, 0 and 1, 0, and L times cosine theta, L times sine theta. Yes, so I think that it is not that beautiful to just draw the line only. So let me just add a little more, 0, 1, and 0, 0. Then hopefully that will add a line, and yeah, so well, it is much better to define certain number for it, but it is just for toy problem, so please allow me just to do in this way. So as you can see that from line numbers 9 to 11, I just pick up 3 corner points, and in lines 13, 14, 15, I just draw the line or side connecting those 2 points. Okay. Then after that, this is x and y is xy coordinate of our the circumcenter, and I will just write down at the end of our script line 19. Then why don't you just learn it, then you can find that. Oh yeah. Yes, this is the one for our simple example, L equal to 1 and 45. So you know that this side length is also 1, and this is also 1, and you know the circumcenter is clearly inside our triangle. Then this one will be the length or the surface area for this edge. Also, that will be the length for this edge. Also, finally, you will have the length here corresponding to this edge. Then, how about this? By keeping 45, the acute angle, and just increase it to 5. Oh, now you will have long side. Then what will happen to this guy? Then of course the theta is still 45 degree, but we will have a very large angle for a different angle or different corner points. So just to do it. Then, wow, what is it? In this case, yes, we have 45 degree. However, we have still small angle here, and here we have an obtuse angle. Then, point is the calculated circumcenter is outside of our triangle. Then what will happen? If we calculate the line, then this one will be the area for our calculation. And how about this? For this node, yes, then that will be the I think that okay. So in my opinion, actually we have to ask square. Okay. So the aspect ratio of our graph was distorted. So that's the reason why I tried to make a normal line by my eye estimation, but it was not that successful. So in this case, let's do it again. So here we have vertical line perpendicular to this horizontal line, and when we have this line, then maybe this would be around the midpoint, and perpendicular line just looks like this. So that will be the length corresponding to this edge. However, for this one, should we assign this length to our control area or surface area for this edge or not? So certainly we should avoid it. So let me think about this one. How about this? If we have square root of 2, then what will happen to our system? Then okay. Then now we have this form. You know that since we have intentionally take the value of L to square root of 2, now we have a right angle here. This is now becomes a right angle, and in this case the circumcenter is just lays on a side here. Then what will happen? In this case, this length should be the one for this edge. Of course, this length is just half of it. So that's the reason why when you previously develop your two-dimensional code, you never care about actually the size. So because that is always given by delta x or delta y, so take just half of it for one side and another half for different side. That was okay. But you know that your previous structured grid can be treated as a special case where all of your triangles are a right triangle whose maximum angle is just 90 degrees. So also for this case, it's okay. Now you can find just half of this line, and in this case we have half of it. So calculating circumcenter is given here, and what I wanted to say is for this case, what will happen? How about the the surface area for this one? If we have this edge, then what will be the surface of your control area? Certainly you have nothing. You have nothing for it. Then let me just slightly increase it to 3. Slightly increase it. Then now you have this obtuse angle. Then now assigning of further values to this edge, that is not reasonable. That should be regarded as ineffective edge. So how can you do that? Just assigning 0 values to your edge. That edge, the edge corresponding to, or edge looking at the obtuse angle. In this case, that should be regarded as just 0 area. Okay? Maybe that sounds a little complicated to you, but you know the mesh is really introducing many unexpected problems, so please understand this complication. As I told you before, this calculation, explicit calculation of coordinates is not done in this recipe shown here. Yeah. So let's go to the 3D. This is the counterexample where the use of structured grid becomes really inefficient. So you know that here you can find 2 different structures, but amazingly enough, both of them try to describe a similar devices. Of course, they are not exactly identical, but they try to describe similar devices. But the difference is, in this case, here on the right side, the mesh is based on tetrahedron. Then it can describe the complicated structure in a nice manner. However, when you go to a structured grid, then you know this is the case. In order to evaluate the shape like this or like this, we have to introduce staggered structures, and we have to introduce many different lines. So in order to resolve the shape here, we have to introduce certain point uniformly or non-uniformly, anyway well divided spacing here. So although your substrate located here is not that much important, but they should be also divided into really dense way. Okay, so I mean that let me just draw again. We have, for example, this form. Yes, let's say this is the form of our calculation, and all kinds of important physical mechanisms only occurs here, 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 and this is just a substrate. If I am allowed to use a triangular mesh, then I would like to divide this part along the shape of our structure. After that, I will just assign very large triangles for these unimportant cases. But if we have to use structured grid, then it is also possible to use it, but it becomes really inefficient. For example, what we can do at best is now I think that I'm afraid that something is wrong with my pencil. Yeah. Now let's say this is the form of our shape of our structure, and in order to resolve this round shape, then we have to assign this form, and also we have to assign this form, this form, this form, this form, this one. Yeah, you know that already this is not as good as as this triangular one to describe our rounded shape. But anyhow, let's assume that it's okay. Then for the all unimportant part, we have to introduce many different lines whose resolution is as good as for these important points. So, you know, in this case, you can easily understand the number of grid points assigned to this type of mesh is much larger than the one with the triangular one. So that's the reason why in reality every time we are using triangular based mesh for two-dimensional structure and tetrahedron based mesh for three-dimensional structures. Okay, so then let me just wrap up our lecture with the last slide. So our last slide related with a really practical one. Calculation of electric field. Consider a triangle. And we know the electrostatic potential at each node. Yes, we know it, and we know it, and we know it. However, quite frequently, we are asked to calculate the electric field inside the triangle. Here we have a triangle. This is one example of an element. So triangle or tetrahedron can be an element. In this case, how can we define the electric field inside it? So that is practically very important question, because although we have not considered any physical modeling for mobility or all kinds of generation recombination, in reality, we have to tweak our physical quantities inside our triangle or tetrahedron. So usually our physical quantities are heavily dependent on the magnitude of electric field inside the element. So always the question is, how can we calculate the electric field? So fortunately, since the electric field is given by gradient of electrostatic potential, so also we can treat our electrostatic potential at any point inside our triangle as this way. So at a certain point R, how can we evaluate the values of our electrostatic potential? The answer is quite straightforward. The answer is, let's say that we have a certain function which has here 1 and 0 and 0. Then we can find a certain function. Let me just use the third direction, the height, as representing the value. This is number 1 and this is number 0 and number 0, and we will have certain function like this. Then also we can define different functions, like having the value 1 for this zeroth node, and all other cases have value 0 here and here. That is possible. Also we can define another one based on the node 1. Here we have number 1 and 0 and 0 for all other nodes. So we can define 3 different basis functions which is attached to node 0, attached to node 1, and attached to node 2. They are just given function of position. Then by using this basis function which linearly varies, then we can say this electrostatic potential inside a triangle can be represented as phi naught. This is not a function of position. This is node potential. This is node quantity times phi naught R plus phi 1. This is also node quantity, and psi 1. This is the basis function defined on the triangle. Also, we can find phi 2, which is defined on 2. Then you can easily calculate this expression, because this gradient operator is really works on a function, not a scalar. So now this phi naught can be easily pulled out, and the remaining thing is just gradient of our psi naught. And also we have gradient of psi 1 and gradient of psi 2. So actually what we have to do for a single triangle is pre-calculate. In advance we calculate gradient of psi naught, gradient of psi 1, gradient of psi 2, the gradient of basis function inside our triangles. then just to multiply our node potential. Then that will give us the electric field vector. Of course, when we need the magnitude, then since we have the vector itself, then calculating its magnitude is not that difficult. Okay, so this is the last slide I prepared. Then see you next Monday. Please prepare your homework number 17 because that is a really important milestone for your final presentation. Thank you and bye.